Hi, welcome back to this tutorial. So in this small tutorial, we'll be just taking a look at the overview of the code which was used in the previous simulation. So ISAC works on this concept of nodes, and each node has a subclass from this class over here called Alice Codelet. So Alice is the namespace where we have all the ISAC libraries, and Codelet is the base class which has methods which we need to override for our own nodes. So the main methods which you override are the start method and the tick method. So start is just called once throughout your application's lifetime, and tick is called repeatedly. There's also a stop method, but that has not been overridden in this case. And over here we have these three ISAC specific functions. So you have macros rather. So you have proto-tx, which gives you the messages which this node will transmit, tx for transmit, and you also have proto-rx, which are the messages which this goal will receive. So goal to feedback proto is the name of the class, that's the name of the structure of this message, and goal to proto is the structure of goal. So both of these proto messages are defined in the ISAC documentation, and the names over here are actually arbitrary. So you can call it whatever you want. You can call it my feedback or my goal. That's not important, but they need to match in other places in your code. The other thing here is ISAC param, which is not used in this case, but you can use it for specifying certain parameters of your node. Alright, so in go to mockup, we can see here that we have the start method, which only runs once, and it causes the tick method to run periodically. Over here it says tick periodically. So this means the tick method just keeps running. You can also specify the tick method to run only when a certain type of message is received. And the frequency of the tick, I think it's specified to be 10 Hertz. I'm not sure where it's defined in this code. Actually, I think it's defined in the JSON, which we'll be getting back to later. So it's quite simple over here. It only has two methods. So it keeps publishing feedback, which tells the simulator whether the robot has reached its goal or not. And it receives new goals, which in the process goal method. So you can see here that it has this function rx goal dot process all new messages. And just to be clear, this rx underscore goal method is auto generated. So depending on the name of the message which we defined here, for example goal over here, it will generate this corresponding rx underscore and tx underscore methods. And that's why you also have tx underscore feedback, like over here, because we named our tx message feedback. And you can have multiple rx and tx messages in the same node. Alright, so this just informs the simulator if it's reached its destination or not. And documentation on how this code works is available in the ISAC documentation. Okay, so now we'll be looking at a few more parts of your application which you need to build to actually build the application. So the first is the build file, and the build file has a list of all the modules and packages which you'll be using in your application. And for example, over here we have multiple applications. Each application is defined as a JSON file, and since we have multiple applications, we have multiple build profiles in this build file, and all of these are built at once. So I'll show you one of these. For example, the one which we've created here is called custom underscore goal dot app dot JSON. So unlike ROS, the thing with ISAC is that you need to specify which topics talk to which ones at compile time itself. And that gives you this kind of mental model of using a graph everywhere. So this is a bit of a learning curve, I believe, but I think it is more efficient than the ROS method of having everything broadcasting over TCP all the time, over a local TCP socket all the time. So for example here, we have some modules which we're importing, and this again is clear from the documentation. And we have the graph. So the graph is important because the graph defines all the nodes which we are using in our application. And as I said before, each node can be thought of as a ROS node, for example. So we have a bunch of nodes here, like the simulation node, the navigation node, the goal generator node which we developed, as well as some for camera and other purposes. And over here we have the edges, and this is where you have to specify which node can talk to which node using which messages. So remember that we created a feedback message in go-to-mockup.hvp over here. So that feedback message is used as an input to the navigation subgraph. So we have the goal generator generating feedback for the navigation subgraph. And similarly, you have other topics which are all connected over here. And which topics connect to which topics all depends on which kind of messages they send and receive. As long as the proto, which is the messages which the sending and receiving are the same, you can connect any node to another node with those messages. And all these nodes run together in parallel. So this is the configuration. So this is the structure. You first have the name of your application, the modules which it has, the graph which contains the nodes, and all the edges. The edges being the messages which each node is sending and receiving, and to which nodes are sending and receiving. And then you have the config, and in the config you can specify certain parameters for your node. For example, for a goal generator node, we have set the default desired position to be 5,5, and we set the tick period to be 10 Hertz. So depending on what you need to do, you can change these parameters at runtime or at compile time over here. So if you remember, we have the NVIDIA website tool, and using website we can change these parameters as well. So that's for the configuration file, and we can see here that, sorry, this must be in the wrong folder. Yes, so we can see here that in this build file that we have multiple packages, and depending on which one we want to launch, only that module is compiled. So you can compile your applications using Bazel, and in case you want to build all the packages in your workspaces once, as you do with ROS, for example, you can do Bazel build ..., and this will compile everything in your workspace at once. But one side effect of this is that it can use quite a bit of disk space, since these ISAC passages tend to be quite large. Alright, so that was a very quick overview of what the code looks like. I suggest going through the ISAC webinar, which will be linked to in the description of this video. And if you have any questions regarding ISAC, please post it in the comments, and I will try to get back and answer your questions as I learn more about the simulator. Thank you.